We developed a PID for the temperature of the muscle tank. We used the thermocouple and the cooler as our PID input and output. The graph does stabilize from the starting temperature, and we found that the system responded quite quickly with minimal overshooting. The PID began to settle after about 45 minutes, and after the full hour it was pretty constant.
As for our web server, we used adafruit.io. Our setup was recording different readings. All of this, we uploaded them in intervals of 10 seconds. The readings we were taking were concentration of algae, the cooler power percentage. We calculated the flow rate dependent on the OD sensor, the temperature of the water. All of this data was very useful because later we would be able to download it and use it for our experimental data. For example, our OD readings to calibrate our OD sensor, and also our temperature readings for our PID.
Our initial design used a tube with 2 water entry points, but it couldn't be fully sealed. We switched to a leak-proof box, drilled 2 holes and fitted waterproof cable glands. An LED and OD sensor were mounted on opposite sides, and several layers of duct tape were used to block out external light. To calibrate the OD sensor, we measured light intensity through varying algae concentrations. As expected, the sensor detected a clear decrease in light intensity as concentration increased. However, the resulting graph produced an R-squared value of 0.8386. This is not ideal, but the OD sensor we use lacks the sensitivity required to provide a fully reliable basis for OD readings in our system.
After repeating the algae growth experiment to account for overnight respiration, we collected concentration measurements over a 24-hour period. Readings were taken every 8 hours, following the initial 16 hours. The initial concentration was 113,298, and the final concentration reached 239,849, slightly more than double. Based on this increase, we calculated a growth rate of 0.74.
As discussed in previous meetings, we addressed the challenge of regulating ammonium concentrations, which is a key biosecurity requirement. While Mytilus acidus is relatively resistant to elevated ammonium, prolonged exposure to levels between 1 to 3 mg per liter can still lead to reduced filtration activity and increased mortality in combination with shifted pH. Simply sending the ammonium back to the algae tank is not sufficient, as without enough turbulence, free algae can't reliably capture excess ammonium, and we have no way of system control of ammonium uptake. Thus, the ammonium might be sent back into the muscle tank. That's why we introduced immobilized algae beads. These gel-like beads made from sodium alginate cross-linked with calcium chloride localize algae in the muscle tank, enabling controlled ammonium uptake through radial diffusion. The matrix protects the cells and prevents overfeeding the muscles if we place the beads in the muscle tank. We tested several formulations and found the optimal morphology with 2.5% alginate and 2% calcium chloride. Each bead holds about 20,000 algae cells, but can hold more if we have a centrifuge. We deployed 85 of those beads into our actual system. Now, the mathematical model showcases that the free algae would theoretically filter ammonium a little quicker. Contrastingly, our experiments using colorimetric ammonium strips showed significant ammonium reduction within 2 hours in bead-treated setups, but none with equivalent free algae. Overall, the incorporation of algae beads for efficient ammonium removal was a successful innovation strategy for modulating and controlling ammonium filtration in our system, and allows for system compatibility across aquatic species' higher ammonium sensitivity.